Thank you. My presentation concerns a study aimed to present strengthening strategies for span of masonry arch bridges. The aim is to calibrate this how to model the material models, so to be able to evaluate the effectiveness of the intervention. I don't spend time to remember how is made a arch bridge, a masonry arch bridge, because many colleagues presented in this workshop. I just want to remember the past where I had some news, my intervention that concerned the upper part of the masonry bridge and what is after over the barrel walls, so the filling and the spandrel walls. As was evidenced by many colleagues in this workshop, also Professor Oliveira just now, the effects of the criticalities of the upper part of the bridges that is characterized by the formation of by the formation of longitudinal cracks that could be in the outer parts, where is the separation between the vault and the external arches, and or in the middle that are mainly that follow the mortar joints. What are the causes of these cracks? The main factors are the temperature, the differential variations of temperature, and also the different coefficients of thermal expansion due to different materials that can constitute the vaults. Then is the thrust exerted by the filling material that is over the vault. Okay, go ahead. Moreover, we can find the cracks, as was made in evidence by many colleagues. I remember Professor Macolini yesterday that emphasized these vertical cracks or diagonal cracks that occur in the spandrels due to out of plane bending. And this is due to thrust exerted by the filling, and also to the low out-of-plane resistance of spandrel that was evidenced also by Professor Oliveira and other colleagues. Some strategies to intervene may concern the application of horizontal and vertical ties, as was shown just now by Professor Oliveira. But it is also another intervention could represent the removal of the filling, replacing it with some transversal and longitudinal walls. This has the advantage to reduce the load, the vertical load, and to reduce the thrust. But is allow these elements allow to maintain the shape, because the walls are elements that are working correctly due to the shape. The external spandrels need to be strengthened, and this due to increase in plane and out of plane resistance. In plane resistance, in plane resistance, because as was put in evidence by Professor Natalino, remember yesterday, his intervention yesterday, but also other colleagues, because due to settlements of the piers, or due to different distribution of vertical load, causes stresses in the spandrels that cause the formation of vertical cracks. And one intervention could be done applying with the application of a mortar coating on both sides, if it's possible. Obviously, if we have to maintain the facade, because as pointed out Professor Oliveira, frequently these constructions are subjected to maintenance by cultural heritage, and so in this case could be applied outside, for example, an hybrid technique that instead of applying the CRM technique on both sides, on one side when we apply the CRM technique using a composite material. In this case we use a GFRP net, and dispersed in a mortar coating. In this case, we can substitute this reinforcement inserting a stainless steel tendons mesh in order to avoid, and this is hidden inside the mortar joints of the masonry. We carried out many tests, both diagonal compression tests for it. We carried out shear compression tests. The scope is to have sufficient information to provide to construct material models. We can see here, this is the behavior of an unreinforced sample. This is applying the hybrid technique, and this is applying the CLM technique, so the composite reinforced mortar on both sides of the masonry wall. And you note a significant increase in resistance. Here we can also see the cracks that in the unreinforced element. The formation is of single cracks, and using this composite reinforcement, we note a significant distribution of cracks, and also we carried out also many tests to check the effectiveness or the increase in performance when subjected to out-of-plane forces. And you can see here the increase in the increase. This is the unreinforced element. This is a simple sample that is subjected to horizontal forces, to cyclic horizontal forces, and here is the result of unstrengthened sample. This is the reinforcement with the hybrid, with the the samples reinforced with the Albert technique and with the CRM technique. We can note a significant increase. Okay. So I just move to here we can see the but I move to the last campaign of tests that we carried out that refer to the volts, and we applied the reinforcement both on the extra dose or at the interdose, just to because in this case what we would like to obtain, we would like to avoid the opening of these cracks that form in the wall, and if we apply on the extra dose or the interdose, we the reinforcement contrasts the opening of the crack, and we note an increase in resistance, a significant increase in resistance, as is evidenced in this graph. This is the unstrengthened wall, and this is the reinforced wall. So what we can see these are the unstrengthened walls, and these are strengthened walls. You can see that here is a lot of cracks form as occur in a reinforced concrete element. So this allowed to have a significant increase in resistance. This study is, as I said at the beginning, is aimed to have a sufficient number of information from experimental information, just to be able to check, to calibrate the numerical models that have to consider the effect of the strengthening, and to be able to evaluate, to assess the effectiveness of the intervention. Thank you for your attention.